Hello. So good evening, everyone. This is a live session. We thought this is a good place to discuss a lot of things. So I think what we are doing is we will discuss a couple of more conceptual things of radio astronomy in terms of last week we covered radio interferometry at great length. Few things are still remaining, so we'll cover that before we proceed. And now we break up this particular today's live session. It will go up to 2 hours, but first hour is we'll go through some more details of the lecture. This everything will be captured and put up in your course feed, and will be available. And slides also will be available. There was a little bit of a mishap that we missed the first few. We couldn't post, or it was not up to date till week 7. Week 8 and week 9 will be up to date today. And so in case there is any issue about the assignment of week 8, please let us know. We'll take it up in the second half. So first we will have this discussion about the concept. After an hour or so, the TA Harsha will come in and show you exactly where all the materials are available one by one, and go through that. Then again, come back after that, the second half of the next hour, and pick up some problems. But in between, you can keep posting and let us know if you have any particular problem with the week 8 assignments. Okay, we can go through that. As we discussed that we will have these sessions, live sessions every week from now onward till the end of this course, that we can get direct contact with all the students and please bring in all the issues, etc. So let's begin with that, and let's see if anybody has a question. Okay, so Asha, are you there?
Yes, sir.
So we can also maybe in the next when we start after we finish this, after maybe you can also discuss a little bit about the forum questions and any issues they have with the week 8 assignments. Okay.
Yeah, sure.
Okay. So just to capture again, we showed that this is we have the single dish, and we know that for a single dish, this happens to me. For a single dish, the size of the dish, capital D, is basically the main thing. So lambda over capital D is kind of measure of something called the resolution. We have done that. As the wavelength becomes higher and higher, the size becomes impractical. So we started something, shifted to something called radio interferometry, where now the single dish size can be replaced by the dimension of the array, or the maximum baseline, which is covered. So if this is B max, then the resolution of this array is given by is proportional to lambda over D max. And that's how we avoid the impractical design. We can make much smaller number of dishes, many of them, and the distance between the largest distance between any two antenna is kind of proxies for that lambda over t for a single dish. And the other part is the effective area, which we can take care of by summing up the area of all the individual dishes. So area of each dish, if it is stated as effective area, the total number of antennas, and this becomes total area of the project. This is with GMRT, we have discussed before. So we go on. So how this works, we have done it a couple of times before, but just for the sake of it, as we go multiple times, things become more effective. So if you have two antennas, you multiply that. We are considering what the multiplying so far. So as we consider a radio source coming from infinity or distant far away field, if it is moving in this direction to both the antennas, then it will appear faster in antenna 2 than antenna 1, and the additional path length converts to directly to additional time, which is given at b dot s, over c. And so this all have been done before. One thing is certain, that as the Earth spins, this source gradually moves and appears in this direction. So at a given another time, the rays will be coming first to antenna 1 and then to antenna 2. And then the delay has to be compensated in antenna number 2. So essentially, all this depends on the direction from where you're receiving the emission. So we did this, the entire derivation. We have E1 dot E2, the output from each antennas. We correlate them or simply multiply them, then do an average on time where the faster varying term goes to 0. All this has been done before. And you retain the slower varying term, or which is function of tau, or this delay. And that is linked with the baseline and the lambda. And that is finally linked with the Earth's rotation. Okay, so that was derived earlier. If you're looking at a single baseline or single pair of antenna, then it gives rise to something called fringe. The frequency of this is given by this thing in the bracket, and that's for 1. Okay. Now, sorry, just one more thing. I think we have done it already. It also depends on this quantity B. So you can say as the baseline becomes larger and larger, longer and longer, this becomes very fast varying term. The frequency increases and it becomes faster term. So for a single spacing, you have this kind of a fringe. For multiple spacing, you will have superposition of multiple of them. So again, the Bmax, in this case, for the maximum baseline, is the resolution, and that compares with the resolution for a single dish. Okay. Questions? If you have any, you can stop me and ask it immediately. This is a session to interact with you guys, so I think feel free to interrupt whenever you can. You can just unmute yourself and ask a question whenever you feel it is going a bit faster or something which is not quite clear. Anything so far? Okay. So yeah. So for different sources at different spacing, you see different fringe. So we can just go ahead. Okay. So just a little bit of a different treatment. We introduce something called Van-Sitter-Zernike theorem. What is it? Now what you have is that uh, for so assume any astrophysical phenomena occurs at a position of R on the sky, and it causes a time variable electric field. Since the source where this electric field originates is in the far field, we assume a convenient location over a celestial sphere of radius R centered on the telescope where it gets recorded. Okay, so you have at a distance, far away distance, there is some astrophysical phenomena occurred, and it created some time varying electric field. Now, since it occurred at a distance of R, at R position of the sky, you assume a sphere that and this telescope at a distance of R where this particular event occurred. Something like borrowing the concept of the celestial sphere. Similarly, so assuming that the space within the celestial sphere is empty, so there is nothing between that astrophysical phenomena and the telescope, then you can write at for the coordinate system R, which is the telescope coordinate system, you can write the electric field which is measured, the electric field which is recorded is linked to the electric field which is which occurs in the sky. And they are linked by this equation, where this is nothing but a propagator. Don't worry about it too much. And just like this, how the far away electric field transforms into the electric field which is measured. We have done something similar earlier. Okay, where did we do? By the way, am I coming in fine, Pasha? I'm audible. Perfect.
Yes, sir. Clear.
So basically, we have done this when we decided, when we discussed the relationship between far field electric field pattern, and the aperture distribution. And we figured out that these two are linked by a Fourier transform. Go back to your distribution. Yeah, so these two are linked by a Fourier transform, and we have shown that for different kind of aperture, rectangular aperture, circular aperture, etc. And so the same thing, similar thing also is linked over here. So you have the field which is recorded on the telescope is just nothing but the electric field in the far field in the sky propagated out. Okay, this is the expression of that. Now, if I just go ahead, so this is a radio interferometer measures not a single field, but the product of the two recordings from two different antennas. So that gives rise to something called a visibility, okay, which is nothing but a product of two electric fields measured by two antennas, 1 and 2. Okay, so this is called the visibility function, which is kind of something like a spatial coherence function and directly related to the average Poynting flux, which measures the intensity of the energy flow of an electric field. Okay, and this gives you the proportionality constant, half epsilon 0 mu 0 there. So if I do that and I express this and I put this expression over here, I can see that this becomes quite cumbersome. So visibility, this special coherence function, is linked to the integral of this epsilon capital R1 and eta, sorry, R1 and eta R2, and the two propagators over there. Now, we can, it is assumed radiation from an astronomical source is not spatially coherent. So this expression is equal to 0 if R1 is not equal to R2. If they're not coherent, then this correlation will become 0. So R1 has to be equal to R2. So if I replace that in the previous expression of this, I finally get an expression which is equal to this. So they originate from the same point. Then only they become correlated. Okay, coherent. So if I do that math, finally, after a few steps, you essentially give rise to an expression like this, where this is the visibility function. V is an integral of A and I and e to the power minus 2 pi, so and so. So if you just do the math, it will be supplied to you. Don't worry too much. Then you can see that slowly you're seeing that this expression over here is nothing but, if I can write, V nu is nothing but a Fourier transform of A nu I nu. Okay. That's what it says. Where A nu I nu is a definition of redefining this particular eta nu R squared. This function is redefined in terms of A and I. Now, A and I have a significance. What is I? I is the original sky brightness. If you remember our first week or second week of lecture, we defined something called a specific intensity. So this I is nothing but linked to the specific intensity on the sky plane. Okay, when talking about the astrophysical sources, and A is nothing but the primary beam pattern, which is receiving this entire information. So V and is just nothing but a Fourier transform of A nu and I. You can also look into the detailed lecture, which also requires this one. So that's essentially what we do have. Okay, now let's redefine the coordinate system on the sky in terms of something called direction cosines, L, M, and N. So L, M, and N has a relationship where L square is equal plus M square plus N square is nothing but equal to 1. Okay, so two of them are independent, one is dependent on the other two, the value. So the two-dimensional image of the sky obtained from an interferometer is projection of the intensity distribution on the sky onto a tangent plane at S0 is equal to L equal to 0, M equal to 0, and N equal to 1, which is the center of the field. Okay. And so if you define that, we are coming to the geometry, then finally this d omega can be expressed in terms of dl dm over 1 minus L squared minus M squared, square root of that. You don't have to worry about this exact derivations, etc. Just remember the final expression that the V and the product of A and I are a Fourier transform pair. Okay, and this coordinate system on the sky represented by this direction S is broken down, is derived in terms of L, M, N which are the direction cosines. That's an easier way to get it. So what we do is, so if I start doing that, then we essentially define the coordinate system on the ground on telescope plane in terms of U, V, and W. Now remember one thing, that this direction S depends highly on the it changes position, right? And the rotation of the Earth kind of influences the projection of this baseline. So finally, all what we measure is in terms of a projected baseline towards the direction of the source. So if the source is rising in the east with the same interferometric baseline, we will have some kind of a projection compared to the source is setting towards the west, then the projection will be changed. So essentially, for a same baseline fixed on the Earth, it sees the sky in a different way based on how the Earth rotates. Okay, so that has to be somehow accounted in when we define this coordinate system for the interferometry. Now that forces us not to just stick to the coordinate system of the antennas on the ground, which is expressed by X, Y, and Z. We have shown this earlier, so last week as well, where Xij, Yij, and Zij is nothing but the XYZ, Xi minus Xj, Yi minus Yj, and Zi minus Zj, corresponding to any two antenna pair given by Y and J. So that is fixed. However, the hour angle and the declination towards the center of the field is defined by H0 and delta naught. While delta naught does not change with time, as the Earth rotates, the H0 do change, because H0 is what? H0 is nothing but the RA naught minus LST. And LST do change as a function of local time. So as the source rises in the east and sets in the west because of the rotation of the Earth, the delta naught is fixed, but H0 changes. So for a given fixed baseline, you have multiple U, V, and W coordinates. Okay, and that's what we expressed in terms of the effect of the Earth's rotation synthesis, which we discussed last time also. Okay, so and also it depends on the lambda. That's a pretty neat derivation. So yeah, so we can skip this. Right. So if you're agreeing with that, then what we derived earlier, the V R1 R2 is given in terms of the Fourier transform of A and I, the product of A and I. Now, ideal case, you can assume that A nu as a function of direction is unity, okay? And then this expression becomes much easy, and it just becomes the Fourier transform of the sky. However, we know for a real antenna, A is not equal to 1 for any direction, and it changes because it has a radiation pattern, which is kind of looks like this. So as a function of theta and phi, the radiation pattern changes. So ALM is essentially has to be measured separately. So if we put all of them together and the actual values of actual expression of L and M, we can recast this expression on the top into this huge cumbersome expression in the middle, which is true for a three-dimensional sky, where there is no assumption about how much is the extent of the field of view, as well as it takes care of the curvature of the Earth and the curvature of the celestial sphere. For both of them, it is taken care of, and this is the total full expression at its glory, where the visibility or the spatial coherence function is nothing but a Fourier transform of the product of A, the primary beam pattern, and I, which is the sky brightness. That's the expression. Now, that becomes, this is not a Fourier transform, sorry, but it becomes a Fourier transform if you do a simple approximation of a small field. So the third dimension of W and N becomes negligible, and this expression reduces to just two-dimensional Fourier transform, where V is a function of U and V, no longer W. That can be ignored, and it is AI, A and I, the product of both, e to the power minus 2 pi I, U, L, and Vm. Okay, times dl/dm. This is nothing but a 2D Fourier transform equation, and also known as the transited Zernike equation. It's a very powerful expression, and the main equation for radio interferometry, where we understand this is the correlation function, which is the output, spatial coherence function, which is the output of the interferometer. And that is linked with the product of the primary beam and the sky. So that gives rise to, if I do both it, I can write it here only. So if I can write the visibility V, I just drop everything else, is nothing but a Fourier transform of A, the primary beam pattern, multiplied with I, the sky. Now, the objective of the entire process is to understand how does the sky looks like. So to make an image of this eye. So that is easy, because now that becomes inverse Fourier transform of the V, right? If I know I, if I know V, I can do an inverse Fourier transform and get V. Okay, and if you know your antenna very well, you can have a prior knowledge of the I, which you can then divide from the image, and you get the final value of I. That's a very oversimplistic way of representing. But that is what to show is that the simple image which was coming for a single dish, that you just have a single dish. Remember that you have a single dish antenna, and you were pointing at different parts of the sky. You made an image by doing a raster scan. Try to motivate that. So if we had a single dish telescope you have a single primary beam. So what you did was you have pointed in one portion, then pointed in the next portion, and the next, and the next. And you made this kind of a raster scan of the entire sky by pointing, right? And for each values, you get something. And then you know that supposedly there's an effort to source at the back, which is like this. So you can sample this and get the image. That's what a single pixel camera represented by the single dish telescope, like green light telescope, for example. Okay. Here, things are a bit different. Here you have a bunch of antenna in an interferometric array, and you are getting visibility, which is a function of frequency, is a Fourier transform of A, which is the primary beam pattern of any antenna, times the sky. So if you have a priori knowledge from electromagnetics about this function, then you can, this is your observable, so what you observe or measure sorry, this is your measurement. This is your measurement. And this is come from electromagnetic theory. If you know your antenna very well, design very well, and this is finally your sky, which you are trying to image. So based on, this is not a single value because you have multiple baselines. So if you have n antenna, you have n antenna minus 1 divided by the number of baselines. Each baseline has different distance. So based on that, you have different values of U and V. So finally, you get that, and then you do the processing to finally derive the value of the image of I. Yes, Akash. Akash, you can go ahead, unmute yourself. Akash, you can, you raised your hand, Akash Kulkarni. You are not audible. Okay, maybe we can move on and we can come back. Maybe it's accidental. Okay. So let's move on. So one more thing we have to discuss is that as we showed, this is again the same picture of the VLA, and what we're showing over here is that for a shorter spacing, you have the fringe which is slowly varying, and for a longer spacing, the fringe varies much faster because the frequency of the fringe omega is proportional to the baseline. So as the baseline increases, the omega increases, and so that is pretty obvious. All right. So you have different kind of fringes. By looking at the fringes, you can say, you can compare and mention whether one is coming from a shorter baseline than the other one. Okay. This is a video. This is the animation which we have created and done in IIT Indore. One of my earlier PhD student created this, and we have to go through it slowly. Yeah, okay, I got Akash's question. So he's asking the question that the question is about the ANU. Can I say it is the effective aperture or is it the FOV? Essentially, it is the FOV. Okay. It is the pattern, the far field radiation pattern, which we know we can characterize it in terms of the the far field pattern. You consider the half power beam width, and that is the kind of FOV. So I think you can consider that to be a FOV. That is fine. Okay, so coming to this expression, let it start from. Let me go back and forth. Okay. Yeah. So see, we will keep it running. It goes in the loops. Don't worry if you miss one frame. So on the left-hand side on the top, we have taken the sky or the eye. That is your eye. Okay. So this is your eye, nu, L, M. Okay. Just a point source. That's it. That's your model eye. We're simulating it. Okay. And this is your antenna layout. So this is your N antenna. And also we are showing how they are laid out. We are varying the number of the antennas from two antennas to 256. Okay. Oh, sorry, 512. And 512 has some significance. We can avoid that right now. It's not important for this, but it is close to some real antenna design eventually. So as the animation progresses, this N ant value goes from 2 to increases to 512. Very well. The topmost panel on the right-hand side is the UV coverage. What is that? Now we know that our values U, V, W is some kind of a matrix rotation of X, Y, and Z. We have done this earlier, right? So this is what the UVW coordinates are for, just a snapshot. So you're looking at one particular direction given by the sky position over here. That's your location. So you know which direction to look. So this defines your S, right? And you know your direction, so you know X, Y, Z. So just simply let the just a snapshot. So you're looking for each antenna, each configuration. You're just taking a snapshot. So you have the UVW values. So you can then do the visibility is a Fourier transform of I simply. So we took the visibility measurement by knowing the UVW coordinates and just inverse Fourier transform it to get the I. But see the difference. So as the antennas goes from 2 to a huge number, you see that the recovered image is finally coming close to what you actually see on the sky. Okay. So what is going on? So when you start from 2, you have only one fringe, then becomes 4. So let's look at it again. Now start. So 2, then 3, then 4, then 5, and so on and so on. So when it was 2, the number of baselines was 1. When the number of antenna became 3, the number of more baseline became 3. Then 4, it increases further, and so on and so on. So as the number of baselines increase, the total number of fringe superposition of that also increases. And so you are able to recover the original extended elliptical Gaussian, which is the closest you can come to a point source. Okay. So that's the Fourier imaging kind of thing. We will post it again so you can keep looking. Let's go forward. So the visibility function and the sky brightness distribution are nothing but a Fourier pair. So your visibility V is nothing but a Fourier pair of the sky brightness I. Here we are assuming, just for the simplicity, that A is equal to 1. Okay, unity. It's normalized, completely flat. Very ideal case. It is not real. So for a point source, the as a flat function, DC. So this is brightness. I wrong. This is the brightness I, and it's the Fourier transform of V, the visibility, and we assume that A is equal to 1. Okay, so if the sky brightness is a point source, just the brightness in the center, then it becomes a DC signal, as we know by Fourier transform. We have done it earlier. There are 2 sources over here with so then it's basically gives a sinusoidal function. 2 sources far away, it gives a bigger function because now the distance is much more, so the frequency is increased. And if you have multiple sources with multiple different brightness, and you have a composite function which gives you like this. You have various different kind of sources, like an extended source looks like this, a Gaussian kind of a thing, and you have different kind of functions on the visibility. So yeah, so you have 2 different sources, extended sources with the distance that gives you a function like this, and so on. So you can have various different kind of pictures which gives you so you have a double source separated by a distance. What is this? If you refer 2 sources, this looks like similar. We'll come to that. So essentially, this is all nothing but a Fourier pair. The visibility given by this and the sky brightness. Here we write it in full glory again. That would be 2D Fourier transform. Okay, which assumption is that the sky is it's coming from a very small region of the sky. Okay, that's doable. So a few more things in this fashion. So we started from this expression. We have the UV distribution. What we can do is that you understand that so what happens is that if you have a fixed number of antennas, there are a fixed number of baselines. So it doesn't have a complete coverage in the UV distribution. It has discrete coverage. So in order to absorb that discrete coverage in the continuous integral, what we define is something called a sampling function. Now, sampling function is very simple. Wherever there is a UV value, the sampling function becomes equal to 1. And wherever there is no UV value, it becomes 0. So it's 0 or 1. Okay. It's just a mathematical way to absorb a discrete function into a continuous function, defining another function which is like a mask. You have a value at some positions, you do not have a value at some positions. Because this your finally the expression of your for expression for your UVW are these are fixed. Okay, they do not have all possible values. Given a set of x, y, z, we have multiple number of UVW, but still not all values. Okay, because it only can produce some set of UVW for all possible H nodes. Okay, not all. So it doesn't, even though it is a kind of a projection, but still it doesn't sample all possible values in UVW plane. So we still have some limited holes, as you see for this one. Even with 512 antennas, which is quite a large number of values, you still see a lot of empty space in the UV UV space. So UV coverage is still not complete. Hence, to account for that, we have a sampling function which gives 0 when there is no value. So if there's a gap, the sampling function S is equal to 0. And if there is a value, like for this particular position, you have a value. So for this or this, S is equal to 1. Okay. Then you can write still this one in terms of integral. So ideally, we would have loved the coverage in the UV plane to be continuous and complete. But because it is not, so we don't have an ideal response for the sky brightness. What happens is, even a fixed compact source appears like a sinc function, and we'll talk about it, because of this missing coverage in the UV plane. Because we are not having a field aperture, we're having discrete antennas which can only fill certain amount of the UV plane and not complete. Okay, so that gives you something called dirty or incomplete coverage. And so it's linked in terms of a convolution. So original sky convolved with something called a PSF or point spread function. It's called point spread function. It will give rise to the first impression of the sky. So if you know the beam or this point spread function, you can recover the original sky. Okay. What this says is the original image, original measurement is not ideal. We have talked about now the measurement as we do the real measurement for an interferometer. The original measurements have some kind of a gain variations because we are finally getting measurements from two different. Remember that we have a simple receiver chain system for a single antenna, radiometer, and we have gain variations for the electronics. So this is the same thing. We are not having any different kind of system. Instead of having one system, we are having multiple systems. Previously, we have only one N system. We have an antenna, and we had some kind of an LNA to amplify, right? We have a down converter, a mixer to down convert, and then again a LPF kind of a thing to cut off, and then finally a spectrometer, etc. And okay. Now every antenna has a similar system. So there are electronics involved, which causes variation in the gain, in frequency, and time. So ultimately, that will affect the visibility which is measured. The observed visibility is nothing but some kind of a gain for each of the antennas times the true visibility. So that is taken care of in terms of something we call as calibration. Please watch the video, original lecture video for this bandwidth thing. They are expressed in details over there. UV coverage we have already discussed, and so we will skip this for this particular session. Just to show you that if you're looking for a VLA like telescope, these are the UV coverage. And for a particular source, if you're looking at a source called 3C147 with a declination of 50, with an antenna which is looking from VLA. So VLA, its latitude is 34° north. Okay, and correctly check. Yeah, it's 34° north, and so this is the different for different hour angle. You can see different snapshots of UV coverages, and that will change. So UV coverage is a tricky business, and it changes as we look at different sources. So that was the source at declination of 50°, and with VLA being at 34°, almost looking at towards the zenith, little bit off. But now, if you're looking with the same same array for a delta equal to 90° sources, like a North Pole, then you see something like this. If you're looking at 60, you're looking like that. If you're looking at -30, almost towards the south, this you see like something very weird pattern appears. This is because of due to the location of the array on the surface of the Earth, you can have different kind of projection towards different parts of the sky. Okay, so I stop here and put it over to Harsha for discussion on the material. We will take I will come back after half an hour and again take up certain topics from the problems which were covered in this particular week. So over to you, Harsha. Stop sharing. Yes. So back in space, take over. Any question regarding this particular part? Please retain the questions. We will come back and answer that in just 30 minutes.
So, good evening, everyone. So, are you able to see the screen? Anyone?
Yes, sir.
Okay, okay, sure. So let's begin, and sorry for the delay. So all the materials have been uploaded. So you have a section called lecture materials where everything has been uploaded. I believe till week 5 or 6, everything has been uploaded, and for 7, it is remaining. We will upload it soon. Uh, Basically, the assignments. Okay, so 6 up to 6, all the assignment detailed answer is uploaded already. You can go through it, and if you feel any thing is means if if at all you have any doubts, then we can have a discussion about it too. So besides that, and I think soon lecture 7 means when the deadline ends for us also, the material for that will be also uploaded. Now, I hope anyone did anybody try to kind of attempt the this week means 8 weeks assignment. Means due date is still remaining. So, did anybody tried it?
Yes, sir, I did.
So did you, is there any problem means concept wise or something which you want to know extra or something? Means or means pretty much I believe most of the questions are straightforward. But still, if you have any doubts, hmm? Mhm. Any doubts?
Sir, actually, I had doubt in question number 11.
11. Okay. 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 So phase of the fringe detected, right? Okay. So you means I think this has been covered, the fringe equation, right? If not, means in this week might be covered, but the fringe equation for that is I believe there is a wait.
Yes, sir, the formula is covered in the topic, sir, but um, the problem is how it differs from question 9, sir. Actually, sorry, question 10.
Okay. Okay. So okay, fine. So question 10 asks you about what is the total means phase difference between two antennas. Okay. But whereas the question 11 asks about the fringe, okay, specific fringe means you know that the any sine wave, what is its limit? It goes from 0 to 2 pi, right? Correct. So if any fringe is occurring, fringe is like what? If you means if I recall something we did in our element means like till class 12, that Young's double slit experiment, the fringe pattern follows like a sine wave, right? So it has a limit from 0 to 2 pi. But whereas when you calculate the fringes from the antenna, means the total phase difference, it will come in or more than 2 pi, means it will come in order of thousands also. Okay, based on the distance between two antennas. Okay, so but the fringe between means whatever the fringe you are is projected on the sky, that will be limited to means like 0 to 2 pi. So that is what is expected in question 11, whereas in question 10, it is expected that the total value, whatever you are getting, that should be there.
Yes, sir. Actually, I solved the question, but still I'm not clear with the concept.
Yeah, that is there, but see, means when we calculate phase delays and everything, so what happens in means actually we calculate more than 2 pi. Okay, then we have to constrain it and come into 2 pi range. So there is a concept called phase wrapping, okay, which which sir will cover. So what happens if you if you are receiving any signal, you are getting a fringing. Okay, so when you do Fourier transform using any FFT functions also, just like a fast Fourier transform, which we saw in Python Python demonstrations. So there you will see that the if you plot the phase, like we plotted always the absolute value ABS values. So instead of that, you will, if you plot NP dot angle, so you will see that angles are always in between 0 to minus pi to pi. It will be always be like that, you will see. But in originality, what is happening, you are going from the source is moving from here to here, the phase is adding up, means like it is going 2 pi, more than 2 pi, okay, like that. So what we have to do, we have to, you will see that the phase is started to climb and suddenly it drops down to means minus pi. So that discontinuity, that means the phase, we have to increment upon that pi so that it will become a linear line, means linearly phase is increasing when your force means when your source is going from one end to another end. Okay, I hope I am means kind of clear about it.
Yes, sir.
Okay. So that's why these things are need to, means if you are means interested in any observations, so you will come around, means the phase is wrapped. Okay, sometimes these terms will come. So means if you are fond of studying some journal articles, so in that also you will say wrapped phases and all those terms will come. So that means that means like whenever you do an observation, but by definition the phase varies from minus pi to pi. But in originality, what is happening, your source is moving means from one portion, means one horizon to the other horizon totally, and the phase is means if you see the projected baseline, the distance is kind of means from here lower to, means one from one angle to other angle, means like it's increasing kind of. Okay, so that means source is traveling, and that should be represented in some positive quantity. So that's why we say that is means like increasing phase. Okay, so and okay, so before coming back to this thing, I would like to go through some forum questions. Okay, in last, I think, live session I missed these things. So means I haven't seen after these, means few question I received before, I think the first live session. After that I didn't saw any other questions. Okay, so one of the question was in one of the example, there is something called 73 degree, means 73 ohms and 50 ohms. We have considered means like this only. So if you revisit this means entire lecture again, so you will see that in this they are discussing about a dipole antenna and dipole antenna. So dipole antenna in general has radiation resistance of 73 ohm. Okay, so based on that, and uh, okay, then another interesting question was means I was expecting this kind of thing, so that here theta 1 and theta 2, why this is taken as equal. Okay, so what happens when we go for approximation, say we have an parabolic dish antenna. So what is the means approximate value of the beam width? Can anyone point it out? Means what is the half power beam width or full width half maximum? Okay, so I believe
Is it
it's proportional is lambda by d approximately, right? Correct? half power
Yes,
beam.
sir.
So this is there. Now the thing is, you can't make means there is always a error in when you are making an antenna, or your antenna is actually rectangular rather than means spherical or parabolic dish. Okay, so in this case, what happens? The beam is also like that. Means it's not completely means identical. Means like a beam like this, and this like cross section is also like this. It's like it has a conic structure. It might have an elongated structure or something like that because of some mismatch or means some space deformations. But when we go for approximations, so what we consider, whatever the half power beamwidth is in theta and same is in phi. Okay, so this is how we approximate. So that's why we consider theta 1 is also equal to theta 2, which is equals to pi by 3. And we approximate what will be the half power beamwidth. So this is how it is calculated. Now, somebody has asked this, means how we came to sinc function. So this is kind of a complete derivation here. For that, so you have means if you go through it, you do the integral, and you have to go for integral by it's one, right? So you have to integrate and put the limits, and you will arrive at sinc function. Sinc function is nothing but sine omega t by omega. Okay, sine x by x. That is what a sinc function is. So moving forward, yeah, this is one more thing aliasing. I think I have covered this in Python when I was showing Python demonstrations for Fourier transforms and all. So there it is covered, but again to have a bit more discussion about it. So what happens whenever you transmit a signal? Okay, so signal can be you don't transmit or receive a single frequency. Okay, you receive band of frequency. If you recall your black body radiation curves, something black body radiation curves looks like something like this. Okay, so you have some visible band over here, and once it decays over the time. Okay, no, decays over the frequency as the frequency increases. So this is frequency. So this is kind of band of frequency, and you in being in the radio range, you just take this part of chunk and try to observe it, what is there in that. Okay, this is essentially what happens. Now you, whenever you see, try to observe or transmit or receive, even when I'm talking, I'm not talking in a single tone. So there is multiple sine waves mixed in my tone. So that's why there is something called voice recognizer or something like that, which recognizes your voice and does means identify you by your voice. Something like that is there. So similarly here also you receive as the Nyquist suggests, what you have means if you have a band of signal, the sampling should be your sampling frequency should be fs should be greater than or equal to your delta nu. Okay, the sampling frequency should be greater than your bandwidth. Now, why bandwidth? Say I am observing at say 1.42 gigahertz. Okay, 1.42 gigahertz, and I have a bandwidth of 100 megahertz. Okay, which is centered around this. Now, according to Nyquist criteria, what will happen? So my fs should be greater than or equal to 200 megahertz. Okay. Now here the thing is, like you say that you are receiving at this, how can you sample at this? So this is because we use something called heterodynamic principle, which was covered in, I think, week 4. Okay, week 4 or week 3. Okay. Okay, so heterodynamic principle suggests you can convert, just like transformers up convert or down convert the voltages what you get at is the AC voltages. Similarly, you can up convert or down convert your frequencies. Okay, so up convert or down convert your frequencies. So since you can down convert your frequency, you don't need means like means sampling frequency of 2.84 gigahertz, more than 2.84 gigahertz. Means if we go by the sampling rate of using this center frequency, so you can down convert, and you know that means the most of the electronics are for low frequencies. Okay, and that is easily available. For high frequencies is also there, but that it is expensive. So means well characterized and cheap electronics are available at this means low frequencies. So you can down convert those frequencies and uh, bring it down to your range. So now say what I am trying to suggest here. Say if I have this much bandwidth, what will happen? So I will say that there will be a signal. Sorry, pardon for that. Make some space. So this suggests what you have a kind of a signal which has some bandwidth. Okay, so you have a bandwidth like this. Okay, so you have a signal which has some kind of bandwidth. Now if you sample it, what will happen? You need to recover it also, right? So you have any signal which originally had a bandwidth, some bandwidth. Now when you sample it and try to recover it again, and this signal is kind of, you have means multiple means same amount of signal coming after one time after another. Okay, so whenever you are receiving from any celestial object, you are receiving it continuously. Okay, so and what you try to do, you try to put out one chunk and try to analyze what are the frequency in it, and then again you means use the another chunk and try to analyze what is there. Now if you downsample it, what will happen? It will confuse that this band and the band means the band next to it is overlapping. Okay, downsampling means like undersampling, when you undersample it. Okay, so and if you oversample it, there will be kind of the next band will have a gap. Okay, so this gap will be there. Now this is what aliasing means. When you means confuse what is what. Okay, so simple thing means the simpler way to understand is in time domain, where say you have a sine function. Okay, now you take only two samples in it. So I will take sample one here and one here. Okay, so if I take two sample, what I can make, so here one will be here and one will be here. So and this will be like going up and down. Okay, so it will be like a triangular wave. Okay, so this is what sine has this frequency of 1 hertz or 1 cycle in a second, 1 hertz. So what I'm doing, I'm sampling at 2 seconds. So in one cycle means in one cycle I am doing two samples. So fs is 2 seconds. Okay, fs is 2 hertz, sorry, 0.5 second. Each 0.5 second I'm taking a sample. So here you can see that when I'm trying to again make a wave, I'm getting a triangular wave, but I can say that okay, this is the representation of sine wave. But if my sampling is say 1.5, so the sample will come. So the sample will come here, and then another sample will be like here. Okay, if my sampling is 1.5, 1.75, say, for example. So if you trace it here, how your sample. So if you do a Fourier transform of this kind of signal, what you will get, you will the means algorithm or the Fourier transform will confuse that whether it is the same signal or not. So that is why the sampling criteria comes, and this is very important because whatever means you are doing means when we study Fourier transform, we study in continuous time. But in actuality, when you are performing on the ground, it is all in discrete. So we perform DFT, discrete Fourier transform, not DTFT. Okay, DTFT has continuous Fourier domain. Okay, whereas DTFT is both discrete in time, both discrete in frequency. So this is done because of the storage purpose. Okay, so that's why the sampling comes. And same is also valid for your UV coverage. The more you sample the UV, the more you sample, the better will be your image. Okay, the better is your UV coverage, and if UV coverage is better, your sampling function means whatever the told right means previously that SUV, this will be better, means like it will have means lots of one means lot means the coverage will be better, and the image which we will get out of it will be much more better. Means like it's similarly like when you see you have seen cameras, right? Cameras, what camera has? Camera has something called means it has a lens, okay, and there is a sensor which is called CCD, which is kept at a focal length. Okay, so the inverted image falls on this, and each sensor detects it and gives a value. And that sensor, the means what the sensor is doing is essentially what sampling function is doing to your means the image. It's like if you have more coverage, you will get a better image. Okay, so I think okay. So with this, we shall go back to the means any questions and doubts till now, or any means clarification on the concepts, which means additional doubts or something which you have.
So can you explain the third question of this week's assignment?
This week's assignment. Okay. Okay. So here, that kind of it's a means very easy question, but what you means here you it is given that means you have a source which is the angles semi-major and major axis or whatever, means your actually the dimension of your source is given. Now you have the means radio telescope, what it means dimension of your radio telescope, and it is said that it is 10 dB tapered on each edge. What is tapering? Means who asked the means like did you means I think in one of the lectures sir told about the tapering. So anybody who knows what is tapering? Hello, I'm not able, right? Huh? Huh?
So tapering means cutting off the radio waves that scatter off the edges of the dish. That
Correct.
is restricting only to the effective area of dish and avoiding the diffraction effects.
Correct. So that means the tapering, correct. So here the thing is saying that your effective area is smaller, okay, and you don't. The question
Sir,
is
you are not
as the
sir, you are
taper.
not audible,
So
sir.
that means a 10 dB tapering.
So you are not
Hello?
sir, you are not audible and your voice is breaking.
Wait, let me. Now it is working.
No, sir, it's breaking.
Breaking. Mm. I don't see any technical problem on my side. Means am I audible? Means like at all?
Yes, sir. Now it's fine.
Am I audible?
Yes, sir. Now it's fine.
Right. Okay, fine. So it's saying that 10 dB taper. Taper means your area is reduced by 10 to the power point. Means 10 to the power point 1. It's like 10% of your area is reduced, and you don't have diffraction. What is you are looking at 3 gigahertz and 30 gigahertz. So I won't say the trick here, but
Sir, your voice is again breaking, sir.
I will say one thing again.
Yes, sir. Please repeat what is said.
So this question suggests that 10 dB is tapered and there is no diffraction due to that. Okay, there is no diffraction pattern. Means consider there is no diffraction. Okay, in that case, find what is your resolution, means angular resolution of the telescope. Okay, at 3 gigahertz and 30 gigahertz. So 10 dB taper means essentially your efficiency is decreased by 10%. So you have 90% efficiency. With that, calculate the uh, resolution of your telescope. So is it clear?
That part I have understood, sir. But can you explain how can we define the angular resolution in degrees for each frequency? That is, here we have 0.3 degrees as the major axis and 0.1 degree as a minor axis. So do we have to find the area of this source by using pi AB formula? Are we supposed to perform like that?
This is you.
Sir, I'm not able to hear you.
Clear.
No, I'm not able to hear you. What you said?
Okay.
Sir, you are not audible, sir.
Sir is back. So what you can do, you can post it on. Okay. Wait. Let me type. Type.
Yeah, I think Harsha, if you turn off your video, you can preserve some bandwidth. Yeah.
Okay. Now am I audible?
Better.
Yes, sir.
Please try.
Okay. So what I'm saying that here you have to find the resolution being tapered of the telescope. That means it is not saying anything about the electrical sources. Say that what would be the expected resolution in degrees or in each frequency. So resolution of the telescope is asked. Okay.
Okay, sir. Now
Hello.
I have understood. Now I have understood what. Yes, sir. Now I have understood, sir.
Correct. Okay. If but today itself. Okay.
Yes, sir. Now I have understood, sir.
Okay. Okay. So I will stop sharing here. Yeah, sir. I am almost done with sharing here.
Okay, thanks, Shasha. I hope now you got to the point where you know where the. So let me just cross check. So all the materials starting from week 1 to week, 7 are all shared, right? Can I say whoever is just one of you, Raghava Krishna?
Yes, sir. All the materials from week 1 to week 7 have been shared.
Correct. And the solutions for the assignments which are closed now, means you have already submitted and the due dates are over. The solutions of those assignments are available.
Yes, sir.
Great. Also, we have a lot of materials like simulations. The Python notebooks of those are also available.
Yes, sir.
Great. Okay, so we will complete 8 and 9. Asha already did a lot of explanation for the week solution of week 8 also, and I think this particular few things now we will also help you to understand. So I hope this works and this will cover all the essential part. So let's start with a couple of examples, and I think probably I will just wait for your reaction, and if not, I will just give you a quick answer. We have already done these things, but we are just, as we discussed, that we will move back and forth and try to cover again different concepts as we are coming close to the end semester exam, and we'll do more revisions as promised. So I think that's what we're doing. So first example is two radio antennas located along the Earth's equator are separated by separated by 30 meters. The baseline is 30 meters, and the lambda is given as 6 centimeters, and hour angle, the H0, is given as 1 hour. Okay. So what is the time delay of a wavefront's arrival at the more distance antenna relative to the closer antenna? Now we know that time delay between two antenna is given by what? B of sine theta over C. Correct? We just we had this discussion earlier. So that's the thing. So you have B sine theta over C. If you just put in the angles, you will get here. All right. So you get the time as seconds. The catch is our angle is 1 hour. Yeah. So the source is then 50 degree. So our angle is equal to 0 when the source transits, right, from the zenith. And it is 15 degree. So when our angle is 1 hour, that corresponds to 15 degree. Why? Because 24 hours covers 360 degrees. So if you do that, you'll find 1 hour equal to 15 degrees. Okay, so you can compute the corresponding time delay. What was the second question? The second question was that what is the phase difference between the parts of the same wavefront? So you have a time delay, you convert it to a phase, and that is easy. So this is what it's given. Okay. Again, look into the thing. When is this second 8-week assignment due? Anyway. So the tau is equal to b sine of theta over c, and 2 delta phi is 2 pi nu tau. So you can calculate that. This comes out to be 258.82 pi radian. Okay. So remember that it takes so full phase. If you have cosine of n pi, again repeats the function, right? N is an integer, so it has a time period repeats. So here we have 0.82 pi as additional. So that's the phase difference we have completed. Okay, with 258 pi is same. Okay, so 0.82 pi radians is the difference. Any issue with this? Hearing none, we go to the next one. Example 2, imagine the source in the previous example located at an hour angle of +1 hour or 15 degrees to the west. 15 degrees to the west of the baseline zenith is a point source with a flux density of 3 Jansky. So based on the expression we can use this. This R is equal to F nu cosine of 2 pi b over lambda sine of omega et. What calibrated value is measured by the 2 antennas acting as a multiplicative interferometer. Then according to the same equation, what are the amplitudes and phase of the detected fringe? Okay. So this is the correlation coming out from the interferometer, multiplying interferometer. So we have determined the fringe phase to be 0.82 radians from the previous example. So the response of the interferometer is 3 cosine of 0.82 pi radians, or so then the Jansky value comes down because you have a fringe function. So that's how it looks like. As a single measured value, this should be strange. The information we can get from this interferometer does not come with a single measurement. We need to measure the output for a range of times to detect the oscillations of the fringes. Although we could not infer the answer to this question from this single measurement, from setup of the earlier example and our calculation in the previous example 1, the part 1 of this example, we know that the amplitude is 3 Jansky, which is already given, and this is 0.8 radians. So that is, we can then calculate what is the instantaneous value of the flux. Now, example number 3, the multiplicative interferometric observation in example 2. How long must we wait to measure one full oscillation of the fringes? Again, it is the same thing. It talks about the fringe spacing. So you have a sinusoidal function. So any integer multiple of pi, it will come to the full period. And so you can calculate from there. So you can go through this as well. Example number 4, radio galaxy Cygnus A contains 2 especially bright points of radio emission, separated by about 0.71 arc-minute. Imagine you set out to build your own interferometer at a wavelength of 6 centimeters and decide to use the bright galaxy to test it out. Over what range of baselines should you make observations of Cygnus A to be able to measure the angular separation between these points? So very clearly, you have two hotspots of the Cygnus, and they are separated by an angular separation of 0.71 arc-minute. And the wavelength is given, that is 6 centimeters. So what do you have? You have a baseline, right? So you have a resolution theta is given by lambda over B max. So you know lambda is 6 centimeter. You know the theta, which is 0.71. So you have to have baselines which, so your baseline has to be higher, larger than the value corresponding to this. So you put in all the values, you convert 0.71 arc-minute radian, you get this particular value, 2 to the power minus 4. So you put that, then baseline comes up to 290 meters. So in order to resolve the source, you need to have a baseline length greater than 20 meters. So this ideally should be, B should be greater than or equal to 290 meters. Because if it is less than 290 meters, then we will not be able to do it. Feel free to ask questions if you have any. Example 5, in an observation of a pair of point sources using an array of antennas, the visibility amplitudes are seen to oscillate with a spacing period equal to that of the expected. That is equal to 1 over the believed separation angle of the other sources. However, the amplitude never goes to 0, oscillating between 2 and 4 Jansky. Why? What does it mean in terms of the sources? So you can use visibility function VAB as FA square plus FB square. You have two sources, and you can kind of derive the expression like this. So maximum occurs when the cosine part will be maximum equals to 1. So 4 Jansky is equal to this, and that is FA plus FB, which is simple. And the negative, most minimum occurs when it is negative. So it goes from, when you have two sources, it goes from FA plus 1, FA plus FB to FA minus FB. So if you have two equations, you have two unknowns, so you can solve for the individual flux density of the sources. Next example, with an astronomical reception system, diverse elements collectively influence the comprehensive noise temperature. This system encompasses an antenna characterized by a noise temperature of 80 Kelvin. So T N of antenna is equal to 80 Kelvin. It operates in an environment with a physical temperature. Ambient temperature is given by 500 Kelvin. Demonstrates the efficiency. So eta is 91%. Additionally, there exists a transmission line functioning at 400 Kelvin, boasting an efficiency. So transmission line is at 400 Kelvin and an efficiency of 90%. Okay. The receiver, on the other hand, comprises of initial 3 stages, each marked by a noise temperature of, so initially 3 stages. So receiver For first one is of 100 Kelvin and gain is 20 dB. The central query pertains to the calculation of total system temperature within this particular configuration. Okay, let's see how to go about it. So there is an antenna which is having a noise temperature of 80 Kelvin. Ambient temperature is 500 Kelvin. Efficiency is 91%. It is connected to the receiver via a transmission line. So an antenna, then connected by a wire or transmission line to a receiver. So the transmission line characteristics given by its ambient temperature is 400 Kelvin and efficiency is 90%. So let us see what are we going to derive. So yeah. So total receiver noise temperature, which has 3 different stages. Each one of them, yes, that was a misreading. So receiver, on the other hand, comprises of initial 3 stages, each marked by a noise temperature of this. So this is true for 1, 2, 3, and gain also is true for 1, 2, and 3. So then we have done this problem before, that you have the how to write it. TR is nothing but TR1 plus TR of 2 multiplied by the gain of 1, then TR of 3 divided by gain of 1 multiplied by gain of 2. Okay, so that's where you finally come out for the total receiver noise temperature given by 101.01 Kelvin. And system temperature, then if you put it about there by all the efficiency parameters, it finally comes out to be 274.96 Kelvin. Okay. Questions here? Let's move on. So in a particular, next example, in a particular observation, we have Umax minus Vmax. Am I audible? Paul? Asha? GB Raghav Krishna?
Yes, sir.
Yeah, great. Thanks. Thanks. So in a particular observation, we have Umax and Vmax is given by 50. Always happens. Yeah. So Umax and Vmax is given by 50 kilo lambda. So they are corresponding to the Vmax, right? That goes to Umax. That is given by 50 kilo lambda. So it in terms of the lambda 10 to the power 3 lambda. Okay, so what is the lambda value? So FWHM is 9 arc minute. So the FOV is half power beamwidth is 9 arc minute. And if we desire to just meet the Nyquist sampling rate with no oversampling and to image the full primary beam of the antennas, what should be the pixel and the map sizes be? Okay. Yeah, so essentially we just discussed this in a bit. So you have when we do the imaging, we have the UV. Okay, so we have the visibility in UV grid. Okay, since the maximum baseline is already given, so that's the extent of the UV values. Okay, so for each pixel, you kind of consider that to be of 1 over twice of this UV values, because that's the inverse in the theta. So you're looking towards in the theta domain. So that is kind of proportional to the inverse of the U max, right? Because U and theta are the Fourier conjugate. Remember, V, which is defined by UV coordinates, is nothing but a Fourier transform of I, which is in the theta, x, theta, y, you can say, or LM, whatever you want to write in angular coordinates. Assuming that the A is equal to 1. It's a special case. Okay. So A is equal to 1, but A has a finite size given by the half power beamwidth. So we will only consider that portion of the sky which is coming from within this 9 arc-minute section of the sky around that point in the center. So, okay, let's go back to further. So U max, we know that is given by 50 kilo lambda, right? Now lambda is, has it been defined? Yeah, so 50 kilo lambda, so 50,000, and twice of that because you are doing a Nyquist. So twice of that. That is given by 2 arc seconds. So delta x or delta y or theta is given by 2 arc seconds. Now to image the primary beam, you have a primary beam size of 9 arc-minute or 9 times 60 arc seconds. So with each of the cells given by 2 arc seconds, you have to simply divide this by 2 arc second. So you have a 9 times 30, that is equal to 270 pixels. Okay. So what happens is that, let me just a little bit take one more slide to explain this particular phenomenon. This may be very bit. Just give me 5 seconds. Yeah, so we can just go ahead. So yeah, so we stopped in that thing discussing that VUV is nothing but a Fourier transform of A LM times I LM. Okay. Now, if I just take it out, assuming this is equal to 1, however, we only concentrate on that part of the sky which is within the half power beamwidth. Okay, but within half power beamwidth also we assume that the response of the primary beam to be equal to 1 or flat. Just a simplification example, simplifying assumption. Sorry, just to make life easier. So you have to only image the part of the sky which falls within the half power beamwidth, and that's it. You don't have to do more than that. Given that, you have now only V, which is a Fourier transform, two-dimensional Fourier transform of sky ILM. Very simplistic assumptions. Now, for a Fourier transform to take place, you know there is something called a fast Fourier transform, which is only applicable if you can grid this data. So what you do is simply you grid the data in a regular Cartesian grid. So you have different values for the grid. So certainly it starts from the center, which is U equal to 0 and V equal to 0, and it extends to the maximum value of U max and V max. Okay, and that is given very clearly from the maximum baseline of the interferometer. There is no doubt about that. That part is very clear. Now, given that, we just take a Fourier transform of that to give to the sky plane, giving the ILM. Okay. So, because it's the fast Fourier transform, so total number of elements. So, suppose this is NU times NV, number of grid points. That will also be equal to NL times NM. So this thing will be equal to that. So NU times NV will be equal to NL times NM. In fact, these values in both axes should be equal. Equal is a square grid in some sense. So the maximum baseline corresponds to what? The minimum in the angular separation, right? That's resolution, right? So there's an inverse. So theta or LM is proportional to 1 over U. Okay. So the maximum of U max is corresponding to the minimum value of the theta. Okay. So what did we do? We had the U max. We calculated the theta mean, the resolution. This is the resolution. We considered the Nyquist sampling, so we made it twice of that. And then with that, we know what is the extent of the beam is. So that was equal to 9 arc-minute. And theta mean was equal to 2 arc-seconds. So we calculated total number of theta. We needed is 270 pixels to image this. Okay. That's the easiest way to understand this one. Questions? We're running very close to the time. We wanted to finish by 8. Just give me another 5 minutes. We will wrap it up. So next example, we have imagined that we wish to use an array with baselines from 10 meter to 30 meter to explore an area of the sky for new sources. If we want to be able to detect sources within a field of view of 10 arc-minute on a site, what constraint does this pose on the bandwidth of the observation? I would say watch the detailed video, which will be coming up tomorrow for this. You can get anything. This will also be uploaded there. Example 9, we want to detect an unresolved source observing at 22.2 gigahertz. A previous 22 gigahertz survey with a sensitivity of 0.3 Jansky did not detect this source. We will use an array of 3 antennas, all with system temperature of 50 Kelvin, effective apertures of 30.4 meters square, observing a single polarization with a bandwidth of 50 megahertz, assuming correlation efficiency of 0.8. if we fail to detect the source, we would at least like to halve the upper limit on its flux density using 5 times the RMS noise as a conservative upper limit or non-detection. What is the minimum amount of time that we should observe the source? That's question number 1. Question number 2 says, what is the minimum flux density that will be detected in the cross correlations for an integration time of 2 minutes? So this deals with something called sensitivity. We discussed a part of it, we didn't go deeper. So sensitivity for an interferometer is given by this, where your system temperature is same as your single dish system temperature. But instead of now, for single dish, we had only T6 over delta nu times delta T. That was given as sensitivity limit. Here we have, for interferometry, we have more number of samples. So that's multiplied by n into n minus 1, which gives you the effect of the total number of baselines. Okay, and there will be some constants, which is given by C. Okay. So if you insert all the values, so you basically have 0.03 Jansky per synthesized beam to match the minimum SNR. If you put on top of that, then you finally get it to observe the particular source for delta T equal to 119 seconds. Don't worry too much about all these things. These are there to make the thing complete. This won't be, this a bit more complex, and we will not make it as a part of the assignments or the final exams. Even if we do, it will be very simple. Don't worry if you don't understand too much. We will try to explain it more in even this week's lecture, as it will be available soon. Okay, so yeah, so the minimum flux density, if you go by this manner, detectable is 0.0518 Jansky. Example 10, we obtain visibility data for a particular astronomical object. A 3D plot of the visibility amplitude is shown in figure A. The amplitudes are shown in the grayscale. U is plotted on the horizontal scale, etc. So this is the visibility data in the figure A is shown here. And figure B shows the amplitude versus the UV distance. What can be inferred about from this particular source? Now you have seen a lot of this 2D Fourier transform pairs, right? So by looking at this particular plot, what can you make up? That's all we're asking. The source is separated by 6.3 arc minute. Sources are, it looks like a pair of sources. The visibility amplitude oscillates with a period of 550 inverse radian. This must compare to a pair of sources separated by 1 over 550 radian. With a peak amplitude of 6 Jansky and minimum amplitude about to be 0, then this gives you the minimum separation of 6.3 arc minute. And two sources of similar, exactly same flux density of 3 Jansky, because it 3 plus 3, we're at the peak. We have seen that example, FA plus FB, when the cosine function peaks, and when it goes to negative, it is FA minus FB. So in this particular case, it is 3 plus 3 to 3 minus 3. That matches, so it is 0 in the minimum and 6 Jansky at the maximum. So that's the two sources, equal surface brightness of 3 Jansky, separated by a 6.3 arc minute. So you can infer a lot from just the visibility plots. That's what I'm saying. Let's look at this 11th example. Let's come close. Yeah, so at another visibility plot, a second astronomical object is observed. Its 3D visibility plot shows an amplitude decreasing with UV distance in all directions. A 2D plot of the amplitude versus UV distance, which is given by this one. It shows about the structure. So it's like an extended source, Gaussian source kind of, which has a the source size is roughly a Gaussian width of FWHM of 1/450, and so that gives rise to 7.6 arc minute. How do we get this 450? It's kind of from where it goes through, from 8-ish to about 4. So it's kind of there, the middle of 300 and 600. So that is 450. So it goes from its peak value of 8 to its half power value of 4. So that's how it is calculated. So FWHM is about 1/this. So you get about 7.6 arc minute. Okay, and the peak flux is about 8 joules. There are two the visibility function for various brightness distribution models. Solid lines, amplitude, and dashed lines are the phases. This is what it is given, and you can take a look. So we have done it also. So Gaussian, displaced Gaussian shape extended. So you can just look at the individual Fourier pairs. It's very self-explanatory. If you look at it, you will understand. We have done it in the previous discussion as well. You just go through it, and when it's available on the portal. Example 13, we learn a new source reported to have an angular size of approximately 3 arc minute with a brighter central core component of about 5 arc seconds. To obtain a reasonable map of this source at 1.35 centimeter wavelength, what baseline length should we use? So again, the same thing, similar expression. So the baselines correspond to about 5/3 of an arc second. The angular size of the source is given by this radian, and the core is approximately 8.07 to the power -7. So that's how it needs to resolve the particular source. So the UV distance is then at the order of this. That corresponds to 15 meter of length at the observing frequency or wavelength of 1.35 centimeters. And approximately 1700 meters or 16.70 meter to resolve the core. This is for resolving the core. So 15 meter for resolving the brighter central core component of about 5 arc seconds, and 3 arc minute is basically the angular size. So as the core is much smaller and compact, you need a longer baseline to resolve that. That's about at 1.35 centimeter is about 1670 meters or 1.67 kilometer is the baseline, and 15 meter is for the just resolving source. Okay, thank you. That's kind of brings close to what we want to discuss and share with you. So I can stop here and ask for any questions you want to have and any discussion on any other topics you want to have in this course. Let me look at the participants. Any questions, Diptangshu, GV, or Sangeeta?
Sir, can you please tell us which are the important topics that need to be covered for the exams? for the final exams?
We'll tell.
Okay.
See, we typically, if you look at the kind of the follow the assignments, right? You typically know by now that what will be the topics. We cover certain things just to make sure that this is mostly for completeness. Then we just give you the assignment. We understand it's a mixed bag of students who are coming in for this particular course. So we keep it simple. We want you to know it's an invitation to radio astronomy, not elimination from radio astronomy. So we want you to get involved. So look, keep a track on the assignments, and that will give you a good deal. But I mean, we will definitely discuss in next week when we will spend about half an hour to discuss. We'll prepare this. Asha, if you can note down. So what topics will be important for the next semester? Okay. Anyone else? Ditanshu or Sangeeta?
No doubt, sir.
Right. Okay. All right. It's been a long time. Thanks for sticking around. See you. Go through the topics which will be all the lecture notes uploaded. And please, any questions?
Excuse me, sir.
Please.
Sir, this is not a doubt, sir. It's just a suggestion, sir. Sir, at times your voice is coming very low, sir. So can you arrange for a physical microphone, sir?
We have right now in this particular class or
No,
even
sir.
in the recorded.
Today was fine, sir. From next week onwards.
No, I mean what I'm saying is that are you finding the same problem in the recorded lectures also or no?
Sir, there were a few lectures where your voice was a bit low, sir.
I see. Okay. Fine, good. I mean, nobody complained otherwise. But yeah, we have a physical mic. Right now, we're talking to a Bluetooth, but we can check. Thanks for.
Okay, sir. Thank you, sir.
Okay. All right. Good night. See you next week. Probably on the same Wednesday. We meet at 6 o'clock. Thank you. Bye-bye. Good night.
Thank you, sir.
Thank you, sir.
Thank you, sir.